So I'm going to be presenting a 2020 paper on shared mental models and how they can be used to improve the effectiveness of human-robot teams. As we move forward, we're going to start moving from seeing robots as just as tools, to seeing robots more as partners. And as these robots become partners, they will be very useful in applications like reconnaissance, search and rescue, where there's a lot of kind of coordination that's required in the team. But according to the paper, one of the perhaps most interesting applications of um, robot partners in a team is space robotics, and this is because the kind of coordination could happen at different locations. There could be a robot kind of on a planet while there's humans in a spaceship, and then the um, the interaction could happen asynchronously. So the robot could continually be functioning while um, in a different location while the human is sleeping, and they somehow need a way to kind of communicate with each other, and the robots might be kind of functioning kind of autonomously. So that makes it even more interesting when the human and the robot do communicate. How can those how can you make that teaming more effective? Um, and so in this paper, it looks at the shared mental model, which is the SMM. And um, so the SMM is just saying that there's a set of knowledge that the team shares. And so this is like a common um, the used term for like human teams, but in the paper, we look at robot SMMs, meaning that you have multiple robot agents and they kind of directly share a mental model. It's fairly simple for a robot because they can just kind of share all the data. There is kind of another SMM that is um, SMM idea that can be um, important in human and robot teaming, and that is the human robot SMM, which is you have a shared set of knowledge between the humans and the robots. So that's not looked at in this paper, but it's definitely an interesting question that is a lot tougher to answer. Um, but in this paper, it's going to focus on the robot SMM and specifically on the SMM hypothesis, which is that SMMs can improve coordination and performance of human agent teams. And um, so the paper looked at some prior work and said, yeah, there is some papers that focus on SMMs, but they don't actually give this solid, concrete evidence that for the SMM hypothesis, because they maybe had some like simulated things or some like you know proof of concepts that like while it seems like the SMM is a good idea, it doesn't actually solidly prove it. And so that's what this or like give solid evidence for it, and that's what this paper sets out to do. And so the paper starts by creating an SMM framework. So it represents kind of all the data of a task using predicate logic. And so that's just saying a bunch of statements that say, like, for example, we could have at AL, which means that agent A is at location L. And so then you have a bunch of different predicates of this form, and then you have kind of logical rules to say if you have this predicate and this predicate, then you must also have this predicate, or you can have um, kind of ideas of like, oh, you can do this if these two predicates are currently in the state, and things like that. And I'll go over that in a bit more detail in some future slides. But um, what I thought about this was that I mean it's really good for kind of making a logical and thoughtful intelligent robot but it's very particular to a task. It seemed like they put in a lot of effort to program this into the robot, and then if you're going to change to a different task, you'd have to do a lot of work from scratch. And so in the future, it would be really cool if that time can be kind of decreased, and so we kind of make a general, some sort of general intelligence for the robot that it can transfer between tasks, and so you don't have to make this huge predicate logic system for every task that you have to define. That takes a long time. But anyways, moving forward, um, so once they created that framework, then they made this simulated fuel repair task, where you had um, these robots on a spaceship with a human, and they're trying to repair some fuel. And so then they took that task and then broke it down into the predicates and um, put it in their SMM framework. And then after that, um, then they actually run the SMM framework using a diarc robot architecture, and so that's just kind of saying we have all these rules now. How do we actually use input from my sensors, and then how do we actually like translate that into motions and kind of send the data along to where it needs to go. And then finally, um, they had those robots running, and they in a simulated environment, and then they had these users um, test it out with their SMM framework, and then they tried to see that if their SMM framework was um, improving the performance of the users. So this is the overview of the task that they modeled with the SMM. So you've got these kind of three different wings, and then you've got two robots that are going around, and each of those blue rectangles is like a fuel tube, and then you can see that some of them are yellow, some of them are red, meaning that they're kind of getting damaged, and so the robots are trying to go around and fix the damaged tubes. And so they have kind of a pre-programmed autonomy routine to do this. They kind of go through their current wing and they check for damaged tubes, and then after they do the survey of the wing, they kind of start fixing the fuel tubes, starting with the one that's most damaged. And then once everything's fixed, they just move on to the next wing. Um, and then you've also got a human in this task through like a VR system, and the human can kind of improve the efficiency of the robots by communicating with them and saying, um, "Hey, can you go to a different wing and repair this fuel tube for me? Um, there's a like it's really damaged and it's causing problems or something like that." Um, and so the idea is that the human needs to be able to do that, but then at the same time, the human is distracted by another task, which is this planetary survey. And so basically, all of the intention of the human is kind of taken up, and we're trying to see if this SMM can kind of improve the performance by of this kind of multitasking human. So now let's look at the how the SMM framework was implemented using the diarc architecture. So um, this is kind of the diagram that they created. And so how it works is we start by the human says something like, "Robot 2, can you come to wing beta?" And then that's sent into the two different speech recognition models. So there's the Sphinx AR, the ASR that kind of breaks, tries to just break down the sentence using like syntax rules. And then there's the Kaldi ASR, which kind of uses more of a classifier approach where it just looks at um, the sentence and then tries to directly turn it into um, kind of something that the robot understands. And um, so the Sphinx ASR is kind of good for very well structured uh, speech, and then the Kaldi ASR is better at something like what we see here. Robot 2, can you like come to the wing beta, so it can kind of work around some of that extra speech tendencies of humans. So then natural language unit will kind of take the two different prediction, what the two different models came up with, and how confident they are in their what they found out from the speech, and then it converts that into something that looks like this. So um, it's this is like the predicate for when the human gives this command. It is proposes human to robot 2 to do the action go to um, uh, for robot 2 to go to wing beta. So it might look a little weird, but that's because it's just kind of a very formal way to represent this for the um, in a way that the robot can kind of understand very logically. Um, And so this gets taken to the goal manager, and the goal manager checks that against some of the rules that it has built into it. So specifically for the action go to, um, we have some preconditions that need to be met. First of all, we cannot be already at the location that we're being told to go to. Otherwise, we'll kind of say, sorry, I can't do that action. And then the other thing is we can't be in the middle of repairing something because I guess it's kind of hard to stop in the middle of a repair. And so assuming that both of those conditions are met, then the new goal of the robot will be to go to wing beta, as we can see on the bottom. So then that action gets sent to robot 2, and robot 2 is now in the state of moving to wing beta. And now, once robot 2 enters that state, we need to update some information about what each of the robots knows. So we update and say, okay, we know that. So we have robot 2 knows that robot 2 is moving to wing beta. And then we also add that robot 1 believes that robot 2 is moving to wing beta. And this is kind of the central question of the paper of, does it matter that we update this robot 1 to know about the kind of state of robot 2? Does this actually lead to better efficiency, or could we just do without doing this update? And maybe we can leave it to the human to update this information by telling the robot 1 if it's important. And so then finally, after the robot has accepted the command, it'll just kind of say, give a little confirmation to the human and say, okay, I'm starting to move to area beta. And that's just for the human to kind of confirm that the right command was conveyed. So then the paper runs a user study to see how this works with real humans. And this is kind of pretty important to, like, it's easy to say, oh, this framework seems like it's helpful and we can kind of show that it has some useful properties, but it's really important to see how does it function with actual humans. And so they ran it with 36 participants, and they have this kind of VR cave you can see on the right. And then in the middle there, you can see there's this planetary survey task where there's kind of the way that worked is like a rover that was giving saying, oh, there's a landmark at a certain coordinate, um, and they'd say that every like minute or so, and then the human would have to mark it on the map. And then meanwhile, at the same time, you have these two robots going around trying to repair all the fuel rods. And so, yeah, the kind of the attention of the human is very split between these two tasks. And so, basically, this whole um, uh, task will end when like the fuel rods reach like some certain critical um, amount of damage. It wasn't exactly clear on in the paper what that meant, but it's something to do with fuel tubes being like damaged and not being repaired fast enough. And so then um, the primary like metric to see how well a participant did is by using score, which is the task time, which depends on how well they did on the fuel tube task, and then multiply that by the kind of accuracy of placing the landmarks in the landmark task. And this way, participants really had to multitask and do both tasks well to get a good score. And then finally, the participants were given like a small performance incentive to just try and do the best that they could. And so now we can take a look at the results. And so the first result is that the score was significantly higher in the case with the SMM. And so remember that the SMM case is where the robots kind of share data between each other and say, um, and so they kind of have all the same information. In the non-SMM case, they have separate forms of information. And so it was found that the score was significantly higher when in the SMM case. So now looking at trying to measure task efficiency, which this paper represented with percentage of tubes repaired and the average tube repair time. And so um, the results kind of showed that the SMM case was a lot better for the percentage of tubes repaired, and it was just a little bit like faster in terms of how fast the tubes were repaired. Um, so there's like a little bit of a improve in task efficiency overall. But the paper also showed that there was not really any significant like decrease in workload or any change in situational awareness. And yeah, so now let's think about why these results were the way they were. So why did the SMM improve performance and task efficiency? So one of the things is that the robots had their pre-programmed autonomy routines, and so um, they could kind of adapt their routines a little bit based on the other knowledge of the other robot. So they wouldn't, for example, be in the same wing trying to survey and fix the same tubes because the autonomy routine would adjust for that. So that's kind of something that the human doesn't even have to be involved with. That's just a little bit of a efficiency boost. So the other thing is that because of this efficiency boost that doesn't require the human at all, the robots don't need to be micromanaged as much. They'll kind of do something intelligent on their own, and they won't be doing anything like clearly um, not optimal. And the other thing that's nice about them sharing knowledge is that when the human asks one of the robots a question like, "Oh, which fuel tubes are damaged?" then the robots can each the robots can like if the human asks robot one, the robot one can say, "Oh yeah, I know that these fuel tubes are damaged," and also robot two knows that these fuel tubes are damaged, and so then the human gets more information out of that interaction and can make better decisions based on that. And so, yeah, both all of those kind of work to make SMM improve the performance and task efficiency. But then, why did workload and situational awareness not really change? It seems like kind of adding more intelligence to the robots should kind of decrease the workload of the human because he doesn't have to deal with all the micromanaging. But according to the paper, they said this task was super demanding and it kind of used up all the humans' cognitive resources, and so when that little bit of time freed up, then the human just kind of put it directly back into better performance on the task. For example, doing more on the planetary survey. Um, and so it didn't actually result in any workload reduction for the human. But it's possible that, like, in a task where um, maybe you don't have as much pressure all the time, it could be possible that the workload does reduce when you add features like this, because then, um, yeah, maybe the human won't be micromanaging as much, and then they can just reduce their workload instead of putting it into better task performance. Okay, so overall, this paper kind of gives the first really concrete results that support the robot SMM hypothesis. But it's important to note that this paper did not show anything related to the human robot SMM hypothesis. So this is where the remember the robot SMM hypothesis is where robots share kind of this mental model, and then human robot is where humans and robots share a mental model between them. And so this is kind of a lot more complicated, and it's kind of a lot less clear of like what's the difference between a human and a robot communicating and like talking to each other rather than sharing a mental model, and what does that mean, and how do you test that with a user study? How do you make robots that can do that effectively? So it's a little bit of a tougher question, but it's um, definitely an interesting question for future work. And something that's really cool in this paper is that their SMM framework can be applied to this human robot SMM question. Um, you might have to make some changes, but it could be applied to that. And um, it also, and this paper also kind of shows kind of some of the requirements to make a good SMM evaluation framework. And so some of those are listed right there. And I think overall, these are pretty fair requirements, because like the paper followed all of those requirements and created a kind of successful evaluation that really seemed to test the hypothesis, and there was no kind of shortcuts. There weren't any like simulated agents where they're like, oh, well, this kind of, I mean, yes, it happened in a simulation, but it's not like, but you had like each of the robots actually going around trying to do things. You actually had humans going in there and testing it out. It wasn't just like a theoretical or proof of concept thing. Um, and then you had like these robots that were doing these autonomous actions and adapting them based on the SMM, and also using that natural language piece, which makes it kind of brings it together and makes it feel very um, kind of it makes it work with the human and not feel very artificial. And yeah, that's the paper.